Today we will be proving the continuity equation using a blue Lowe's bucket. Let's get started. So here's my setup. I have a 5-gallon bucket that I have drilled a hole in. I will fill it up with water to a measured height, then remove some tape I have covering the hole and start my timer. The area I have marked with orange is our controlled value. Before starting our calculations, it's always important to ask yourself, is it steady or unsteady, and does it have uniform flow? This helps us choose to which form of the continuity equation we need to use. Now what are we dealing with? Since we have an outlet but not an inlet, this causes our water level to change with time. This defines a non-steady state. Now for if it is uniform or not, this can get pretty confusing since the velocity isn't technically going to be constant, since as the water level drops, the velocity will also drop. But at any instance on the cross section, we can assume the velocity is constant, making it a uniform flow. Now getting to our calculations, it is important to know where we will be getting our velocity term from, which happens to be good old Chapter 5's Bernoulli equation. Known values are pressure at point 2 being 0 since it is open to the atmosphere, velocity at point 2 being 0 even though it actually isn't, but the velocity at point 1 is much greater, so we can assume it's about 0. A good way of deciding if you can do this is if your outlet at the bottom is at least 1/10 smaller than the diameter of your tank, which in this case we have. Your pressure at point 1 is also 0 because it is open to the atmosphere. We write down the Bernoulli's equation, mark out the step that goes to 0, and solve for the velocity term. We do not plug in numbers at this moment because we will use this to integrate. On to the continuity equation, we have known and measured values, height equal to 10 inches which I measured from the bottom hole to the water line. Diameter of the bottom hole, which I will write in a lowercase d, was drilled with a 1/2 inch drill bit. The diameter of the bucket, written in capital D, was measured out to be 11.5 inches, and we know gravity is 32.2 feet per second squared. The continuity equation goes d dt mass in a controlled volume is equal to the sum of the mass flow rates in minus the sum of the mass flow rates out. We don't have any mass flow rates in, so we get rid of it. We expand our mass flow rates, cancel out like terms on both sides, and we are left with the differential equation. We split it up, putting it a dH and a dt on both sides, and then take the integral. After taking the integral, you are left with one unknown, which is t1. You solve for t1 and get about 118.7176 seconds, or 1 minute and 58 seconds. Now it is time to test it. You can see that I will go to pull the tape off my bottom hole and start the timer at the same time. This is to improve the accuracy of the test. I will speed up this part of the video so that it can all fit, but the camera will never move to prove that this was a live shot. At this point in the experiment, you can see there has been a big decrease in the velocity of the water leaving the hole, which corresponds to the water level dropping. As you can see, I am putting my finger over the hole to show that the water is still coming out. I measured my 10 inches from the very bottom of the hole to the top of the water level. So to get accurate results, I want to make sure that the water level is exactly where I measured it. So I'm going to call it quits to the test around 2 minutes and 5 seconds. So to conclude this project and the semester, my time calculated was within 10 seconds, which makes this project a success. Thank you for everything you did for us through this crazy semester, and have a good one.